Okay, so today I'm going to tell you about polynomials, which are an important tool in math and computer science, and we'll see them used several times in theory of error correcting codes, communication complexity, cryptography, number theory, and so forth. So before I tell you about polynomials, I have to tell you a little bit about a mathematical concept called fields, which is a little bit related to the number theory that we did a couple lectures ago. So polynomials like to live in fields. This is a nice picture of a field, but it's not the mathematical notion of a field. The mathematical notion of a field is a kind of number system, and so I'll tell you what that is now. Before doing that, there's a nice little quote that is perhaps a little bit relevant to us about a particular field that is the computer scientist's favorite field, f2 to the k, where 2 equals 0, plus is minus, and squaring is a linear operation. So, well, it's a number system where things are not quite as they seem always. This quote's due to an interesting guy, Rich Schroepel. He was kind of like a hacker guy at MIT in like the 70s. He invented some candidates for AES and SHA that were not eventually adopted, but they were good ones. He was also the first person to recognize that factoring can be done in sub-exponential time. He gave an algorithm that runs in like 2 to the square root of the bit length of the number. Okay, well, enough about him. Let me tell you about fields. So basically, I mean, I'll be a little bit informal. A field is like a number system where you can do the 4 basic operations of add, subtract, multiply, and divide by non-zero numbers. Okay, and where all the most basic laws of arithmetic apply. So the fields that everybody is most familiar with are these fields. The real numbers, it's a good field. Rational numbers is also a nice field. You can still add, subtract, multiply, and divide rational numbers and get rational numbers. There's also the complex numbers, where you can still do all these same operations. And we may or may not encounter them when we talk about quantum computation later in the class. And more interesting one, or another interesting one that we saw essentially a couple lectures ago, is the set of integers modulo a prime number, which we denoted by z sub p. And you know, it's not too hard to show that you can add and subtract and multiply like normal in the integers modulo a prime. But more interestingly, we observed that you could also divide, that every number other than 0 mod a prime has a multiplicative inverse. Here are some examples of number systems that look like they could maybe be a field but aren't. So the integers, so what is the problem with the integers? Yeah, you can't divide. I mean, sometimes you can divide and get lucky, like 6 divided by 3 is 2, but if you try to do 3 divided by 6, then you do not stay inside the integers. And how about the positive reals? Yeah, of course, there you have a problem with subtraction. Everything else is good, but if you subtract 2 positive reals, you might not get a positive real. Okay, so I'll more or less define fields rigorously here. But in general, I mean, if you have a field, it's just like a set of numbers. And then you have to have 2 notions, addition and multiplication. Because like we saw with the numbers mod of prime, like once you define addition and multiplication, you can define subtraction and division to be their inverses. And you can imagine just giving the addition and the multiplication by tables. So for example, here's the field. It's integers mod 3. And it's like a notational convention that when you decide you're talking about fields, you use an f instead of whatever, a z. So we're going to write f3 to remind ourselves that it's a field, but it's the same. It's the integers mod 3. And you can just say, like, OK, it has 3 things called 0, 1, and 2 in it. Here's the rule for how to add, and here's the rule for how to multiply. OK, and you can figure out, for example, how to divide by, you know, to take the inverse of 2, you look along here until you find a 1 in the row. And then this column is the inverse. OK, so here's the fine print of like what you need to be a field. I'll even say it. You have to have that addition and multiplication are associative and commutative. You have to have a number called 0, which satisfies 0 plus x equals, that's a typo. It should say x, naturally. The field should also contain a number called 1, such that 1 times x is x. And all the elements have to have a negative and a reciprocal. And you need that, multiplication distributes over addition, like a times b plus c is a times b plus a times c. So, well, anyway, all the fields I'll talk about will have all these familiar properties, and you don't need to stress yourself about them, but this is the fine print of what counts as a field. Any questions so far? Okay, so we saw some familiar infinite fields, just fields where there's infinitely many numbers, the rationals, the reals, the complexes. And we also know some finite fields. These are number systems with only finitely many elements where you still have all these basic 4 operations defined. We saw the integers modulo a prime, which we decided to now call f sub b. So is there a field with 2 elements? Yes? Okay, good. Is there a field with 3 elements? Yes? Is there a field with 4 elements? Okay, what is it? What's that? Homework. I don't recall it being on the homework. Maybe there's like a homework that I did not notice, because every time I talk about this, people say that like some similar thing was on the homework. Well, the answer is yes, and here it is. I call this F4, and I'll say it has 4 elements in it, 0, 1, and A and B. And these are the addition rules, and these are the multiplication rules. And it's not necessarily so clear that it's a field, like really you have to check all those things, like addition is associative, and multiplication is associative and commutative, and there's inverses and everything. Well, you can check it, and I can even probably later explain to you more easily why this is definitely a field, but in any case, there's a field with 4 elements, and this is it. Is there a field with 5 elements? Yes. Integers mod 5. Is there a field with 6 elements? Well, I don't know. Maybe you don't know. It turns out the answer is no. A field with 7 elements? Yes. Is there a field with 8 elements? Maybe. Turns out there is. Is there a field with 9 elements? You'll see on the homework. Maybe. But yes, there is, it turns out. Is there a field with 10 elements? No. Okay, so can somebody guess the rule? If you haven't seen it before, what is the fact of life? It's a pattern. Does anybody know? Yes? Well, you had. I don't know who started talking, but I was pointing at someone else, but maybe they weren't. Yes?
It's not when the number of elements is like the product of 2 primes?
Something like that. Yeah, it turns out that there's a field if and only if it's a power of a prime. And actually, interestingly, it has the property that like for every number q, if it is a power of a prime, there's basically only one field that has that number of elements. What do we mean by that? It means that like if you have 2 different fields that have that number of elements, they're really the same thing if you just rename the elements. In other words, there's a way to rename the elements so that the addition and multiplication tables are the same. So really, up to how you name the elements, whenever q is a power of a prime, there is a field of that size, and it's unique. And it's usually written f sub q. Now, you would say to me, like, OK, if q is a prime, I know what this field is. It's the integers mod that prime. But if q is a power of a prime, like, what is this field? Like, how do I get these addition and multiplication tables? It's a little hard to describe. It's not like impossible, but in fact, I'll kind of tell you later. But for the purposes of this class, you only need to know about the fields, which are just integers mod a prime. So I wanted to tell you this fact about the other finite fields, but you don't need to worry about it too much. Yep?
What's the distinction between a field and a group?
Oh, it's quite a, I mean, we didn't talk about groups, but a group is just a, I guess, a system of objects with many fewer laws. It basically just needs some kind of notion of a multiplication. But fields have addition and multiplication and division, and they're associative and commutative, and like the distributive law holds. So it's like there are many things that need to happen to have a field. And maybe that's why there's not that many of them. There's kind of like 1 per prime power, and that's it. OK, so that was just a little story about fields, which will serve as the basis for the main topic today, which is polynomials, which is something I think you've probably heard of before and know a little bit about, but we'll see some interesting things about polynomials today. Any other questions about fields, by the way? OK. I mean, the too long didn't read is that, like, the integers monoprime. You can add, multiply, subtract, and divide. OK, so polynomial. So polynomial, it's basically an expression that looks like this. I mean, this is a polynomial. And for now, you should even think of it as like a syntactic object, like kind of like a string, you know? So there's this symbol, x, and that's called the variable. And it appears a few times with powers. And then you got these numbers standing next to the powers, and they're called coefficients. OK? And these numbers, these coefficients, they can come from any field. So whenever you're talking about polynomials, like the coefficients, which you think of as numbers, come from a field. And actually, polynomials, I mean, you can more generally talk about polynomials that have more than one variable. But in this lecture, we'll just talk about polynomials with one variable, which we'll always call x. And here's some notation that I will use. If you have a variable symbol x, and you have a field f, which is where you want the coefficient numbers to come from, the set of all polynomials with variable x and coefficients from that field is written f square brackets x. So for example, this thing is in the set R, that's the reals, square brackets x. Because these are all real numbers. Actually, it's also in C square brackets x, because I guess technically these are all complex numbers too. It's also in Q square brackets x, because if you squint enough, these are actually all rational numbers, the coefficients as well. OK, so here's a more formal definition of polynomials, which I'll present, because it'll let me make a few more definitions. So let f be a field, and let x be a variable symbol. So f of x, f square brackets x, is the set of polynomials over this field. And what that means is the set of all expressions that look like this. You know, you have some CD, which is supposed to be a field element, times x to the d plus some other field element times x to the d minus 1 plus dot, 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 times the x squared piece, the x to the 1 piece. And you can think of this as like x to the 0, c0 times x to the 0. And just for what I'm going to say next, we want this top coefficient to not be 0. Basically, because I want to say the degree of this polynomial is defined to be d. It's like the highest power that doesn't have a 0 coefficient at the front. Is that OK? Now, actually, if you have an extremely logical mind and you look at everything that I've said so far, then I'm missing one polynomial. Because I also let the expression that's just 0 be a polynomial. You know, that's a popular polynomial, the polynomial that's just 0. And its top coefficient is not non-zero, because everything is 0. So basically, the 0 polynomial is a bit special. It doesn't really have a degree. I guess for the best convention is to call its degree negative infinity. But like, don't get too hung up on that. I mean, maybe an equally good convention is just to say it doesn't have a degree. But sometimes if you decide to call its degree negative infinity, it makes some statements of theorems simpler. Yes?
How is it different from just constant, non-zero?
Oh, great question. So if you have any other number, like 5 is also a polynomial. That's a polynomial of degree 0. That's the case where all this stuff is 0. And then this last guy is an actual non-zero number, like 5. And that's a polynomial of degree 0, also called a constant polynomial. It's just fishy, like when that constant happens to be 0, then then it's not clear what the degree is supposed to be. But for example, with this convention, you can say if a polynomial has degree less than or equal to 0, then it's a constant polynomial. But again, that's just some trickery. Yeah. Any other questions? Does that make sense? OK. So next thing I want to talk about is adding and multiplying polynomials. And the story here is that you can add and multiply polynomials. It's kind of the end of the story, but I'll show you. Here are two polynomials in f11 square brackets x. Okay, so that means the polynomials, the variable is x, and you think of all the coefficients as being, numbers mod 11. So here they are. This one has degree 3. This one has degree 2. And you can just say, hey, p of x plus q of x is another polynomial. I just added it all up. And this is fine. You see here I got a coefficient which is 15. So it's somehow nicer to say, well, ooh, they're mod 11. So this is maybe it might be a little better if I had written equivalent mod 11 here. But eventually we just say, well, it's equal to this. So I took this coefficient mod 11. And I can also do the same thing for this one. Minus 1 is like equivalent to plus 10 mod 11. Okay, so I just added these two polynomials. I got a new polynomial. Okay. Actually, one thing I'll just mention, if you have two polynomials of degree d1 and d2, and you add them, the new degree is at most the maximum of the old degrees, because you never get any higher powers. Okay, you can also multiply them, and it works just as you expect. So this p times this q, you just expand it all out, collect up the like terms, and then you can reduce all the coefficients mod 11 if that's what your field is. Okay, any questions about that? Okay, now let's check out a few facts about this adding and multiplying polynomials, because something cool could happen. So polynomial addition is associative and commutative, and there's a zero polynomial. We talked about the zero polynomial, and if you add it to any other polynomial, you'll get the same polynomial. You can subtract polynomials too by negating all the coefficients, negates the polynomial. Multiplication is associative. It's also commutative. There's a polynomial called 1. It's the degree 0 polynomial that just has 1 as its only coefficient. Multiplication distributes over addition. So actually, I mean, this is collecting a lot of cool facts about the set of all polynomials. And you might think, hey, wait, maybe the set of all polynomials is also a field. That'd be awesome. But it's not true, because you can't divide polynomials. I mean, you kind of can, but like it's not like the result is always a polynomial if you divide one polynomial by another polynomial. It's like q of x doesn't necessarily divide evenly into p of x always. Actually, if it were, then it would be a field, which would be cool, but it's not the case. So let's say a few things about this division of polynomials. So this is, a basic sad fact that if you take two polynomials, their ratio is not necessarily a polynomial. Sometimes it works out, but not always. And so it's not quite a field. It's some other thing, some math term, a commutative ring. But it's very similar. The point I want to make is it's very similar to the integers, right? The integers are kind of great. They're like you can almost do everything. You add, multiply, subtract. You just can't divide with the integers. It's similar with the polynomials. In fact, there are many, many analogies. It's quite interesting. There are many analogies between the set of integers and the set of polynomials with coefficients in a field. Yeah?
Can you not divide by them even modded? I mean, with the integers, if we mod them, we can divide. But if you have like a polynomial mod 11, you still can't divide?
You can't necessarily, yeah. I'll show an example, but I'll also talk about this. Yeah, I'll show a few things and then ask me again. So actually, let me tell you about these analogies, these interesting analogies between the set of integers and the set of polynomials. So even though you can't divide with the integers in the sense that, like, an integer divided by an integer is not always an integer, you do have some other kind of division, this division with remainder. We talked about it a couple lectures ago. Namely, if you have a and b is not 0, you can try to divide b into a, and you get a quotient q, and you get a remainder r, and it has the property that r is like smaller than the thing you're dividing by, right? I mean, that's division with remainder. And you have the exact same concept with polynomials. I'll show it to you. If you have two polynomials a and b should not be the 0 polynomial, then you can divide b into a and get a quotient and a remainder. You can write a equals q times b plus r. And again, this remainder will be kind of smaller than the thing you're dividing by. But smaller means here it'll have smaller degree. Okay, so you can divide and get a remainder whose degree is smaller than the thing you're dividing by. So here's an example. Again, to actually follow this example, you have to remember how to do long division of numbers, like in grade school, which is a little tricky. So suppose I say, OK, this is my favorite example field, F11. So we're going to have these two polynomials, thinking of them as polynomials with coefficients mod 11. And I want to divide this one, 6x to the fourth plus whatever, by this one, and get a quotient and a remainder. So I'll just do it. You write it down like this, and then you kind of say, all right, like what's the largest multiple of this first largest kind of digit or whatever, largest piece that goes into this largest thing? It's 3 times x squared. So then I multiply this by this. It's only semi-important for you to follow this calculation. It's sort of just for an illustration. And I get this times this is this, and then I subtract them, right? And then I get this. And you know, this minus x squared is the same as 10x squared, because minus 1 is 10. But I'm not even going to worry about that right now. But I should multiply this by 5 to get, well, you get 10, which is negative 1. Anyway, you subtract this, and that's the end. This is the remainder. So you can maybe review this at home. But the point is, what I've just computed is that this is the quotient. This is the remainder. I've checked that this times this plus the remainder is the big thing. This is all mod 11. And you can also check that this remainder, has degree smaller than the thing we're dividing by. Because basically, I can keep going with this division process until like the degree here is like smaller than the thing I'm dividing by. OK. So now that we've seen that, I can tell you all these analogies. So in integers, we have a notion of size, which is just the absolute value of a number. In polynomials, we have a notion of size, which is the degree. There's this division thing in the integers where you have a quotient and a remainder, where the remainder is smaller than what you're dividing by. Same thing in polynomials. We just saw that. So actually, once we had this over the integers, we talked about Euclid's algorithm, which can find the GCD of two numbers. And you can use literally exactly, 100% exactly the same algorithm to find the GCD of two polynomials. And in the integers, we have this notion that a number is prime if it has no non-trivial divisors. And there's the analogous notion in polynomials. A polynomial is called irreducible, or prime, if it has no non-trivial divisors. This also you don't need to know. I'm just sort of telling you for fun. And what we saw is that if you take the integers and go mod a prime, you get a field. And actually, the same is true with polynomials. This is kind of interesting. If you take the set of all polynomials and you sort of like always mod them out by an irreducible polynomial, you get a field. And this is actually how you get to all those other finite fields that I was telling you about. These fields of size, a prime power, not just a prime, but a prime power. You get them by this way of constructing them. So it's kind of like a generalization of the way we constructed the first fields, first finite fields. But as I said, this is actually more just for interest's sake, and you don't really need to know about this. But I wanted to mention it to tell you how you actually get these other finite fields. Any questions? Yeah? The remainder for the polynomial division? No, it's unique. It's unique.
Like the last example, if we don't it's not 3 x squared plus 5. We don't plus the 5. We can still get a remainder of like 3 less than.
No, I think it should be unique. I mean, well, come to office hours. We'll do an example. Yeah. OK. So that's enough theory of algebra. Let's talk a little bit more about things you can do with polynomials. So actually, so far, if you think about it, we only talked about polynomials really as like syntactic objects, like strings, with numbers and symbols. But you're probably more used to this other common thing you can do with polynomials, which is like evaluate them. Okay, so given a polynomial p of x, and if a is also a field element, you can like plug a in for x and get like a new field element. That's called evaluation. So if this is our nice polynomial in f11, bracket x, and we can plug in like 6. We can evaluate it at 6, and then you just plug it in for x and do the computations. All these are like numbers now in the field. They're just integers mod 11, and you get a result. Okay. Or you can plug in another number, you'll get another result. So this is p evaluated at 4. And you can do this for a while, and you have the most fun when you plug in a number and you get 0. That's like your favorite thing to happen. When you plug in a number and get 0, that number is called a root. Okay, so R, we say, is a root of a polynomial. This is a field element. If when you evaluate the polynomial at that element, you get 0. Okay. So here's a little fact about polynomials. We'll see a more interesting version of this fact later. We'll call it a theorem. Let's say you have a polynomial and it has degree 1. That's linear polynomial. Then the theorem is that it has exactly 1 root. Okay, let's prove this. Here's the proof. It's pretty short. So let's say p of x has degree 1. So it has just only powers of 1 and 0. So we can write it as cx plus d. And c is not 0, because otherwise it would have degree less than 1. And what would it mean if p of r is 0? It would just mean that c times r plus d is 0. And then you can like solve this for r as follows. I mean, in a field, the good thing about a field is you can subtract and add and divide like you always do. So c times r is minus d. And then c is not 0, so I can divide by it, and I get that r is minus d over c. Okay, and these are all if and only if. So that's it. Okay. Okay, so buoyed by that great theorem, degree 1 polynomial has 1 root. We might be like, let's go to degree 2, see what happens. So potential theorem, let p of x be a polynomial of degree 2. Then how many roots does it have? Yeah, you might say 2 sounds like it would be an excellent answer. But let's think about it for a second. Here's one of my top polynomials of degree 2, x squared plus 1. But actually, I didn't tell you what field it was in yet. I mean, the coefficients here are 1 and 0. And actually, every field has 0 and 1. So actually, this can be a polynomial in any field, over any field. I didn't tell you yet. So let's take this polynomial, but let's imagine that it's in f2x. How many roots does it have? You can check this by brute force. There are only 2 possible elements. So how many roots does it have? 1. Yeah, 0 does not give you a root, but 1 does give you a root. Okay. It's also the same mod 3. How many roots does it have? Can somebody quickly compute by brute force? Anybody? Yes, it has 0 roots. That's weird. Mod 5? Well, I'll just tell you. I mean, this is our next easy field. Has 2. 2 squared plus 1 is 0 mod 5, and 3 squared plus 1 is 0 mod 5. So looks like anything can happen so far. Over the reals? Yeah, nothing. 0. Over the complex numbers? 2. Yeah, if you know your complex numbers, I and negative I. So seems like there's lots of possibilities, although we never found more than 2. And that's the theorem. So this is like, I should have put like the blink tag on this. This is like the most important theorem of all that has anything to do with polynomials or algebra. Anything that has to do with algebra, just always use this theorem. Okay? If you have a polynomial and it's not the 0 polynomial and it has degree d, then it has at most d roots. You'd be surprised at how often you can use this theorem to prove everything you want to prove. Okay? For example, like this is like the key, well, one of the key theorems in that Agrawal-Kayal-Saxena polynomial, or sorry, primality algorithm. Just this awesome theorem. I was thinking of like having like another slide that just said the exact same thing to emphasize it, but I took that out. So that's an important theorem, so let us prove it. It's going to fit all on this one slide. Well, the proof is by induction on D. And the base case is when D is 0. And the good thing, we talked about degree 0 polynomials. So degree 0 polynomial is a polynomial that's just a constant. It's just a for some coefficient a. And this theorem is always about non-zero polynomials because, of course, 0 polynomial, everything is a root. So ignore that. So a has to be non-zero. So it's just like p of x equals 5. And of course, that has 0 roots. I mean, whatever you plug in, you get 5, which is not 0. So the base case is done. We actually also did the next case, d equals 1, a couple slides ago. But anyway, we'll just start our induction now. So let's assume that this theorem is true for all d. And now we're going to prove it for d plus 1. So let p of x have degree d plus 1. OK, so there's kind of some cases here. If p of x happens to have 0 roots, I don't know, it could happen, then we're done. 0 is less than or equal to d plus 1. OK, that's a bit lucky. Otherwise, it has some root, at least one root. And let's call it b. In other words, p of b is 0. And now we're going to use this great division algorithm that we like so much. The key is to take p and try to divide it by x minus b. X minus b is a polynomial of degree 1. And I'm just going to apply this division algorithm. I'm going to try to divide x minus b into p. So I can do that with the long division or whatever. And I'll get a quotient, and I'll get a remainder. And what is the thing that we remember about the remainder?
Degree is less than q.
Yeah, it's not less than q. It's less than the thing you're dividing by. So the degree of r of x is less than the thing that I'm dividing by. What is the degree of the thing I'm dividing by? No, 1. That's the highest power is 1. So therefore, the degree of r of x has to be less than 1. So either it's 0 or it's, sorry, yeah, the degree is 0. It's a constant, or it could be the 0 polynomial. But in any case, r itself would have to be just a constant. It would have to have no x's. OK, so it's just r of x would be a constant field element, number. Let's call it little r. So p of x is actually just q of x times x minus b plus some number r. OK, now I haven't even used the fact yet that b is a root, so I'll use that now. Since b is a root, when I plug it into p of x, I get 0. That's the definition. But this is equality, so I'll plug it into the right-hand side. I get q of b times b minus b, so that's 0, plus little r. So that proves that r is 0. So it basically proves that actually when you do this division, like, you don't get a remainder at all. It divides evenly. So p of x is actually just q of x times x minus b. And now actually what I want to claim is that the degree of q is d, the quotient, because it's not even really so much hence degree is d, but p has degree d plus 1. So the highest power of x in p is d plus 1. And then I take some polynomial q with its x's and so forth, and I multiply it by x minus b. So I mean, q is got to have like a power of x to the d in it. So that when you do this multiplication, you get the power of x to the d minus 1 here. So the degree of q is d. And so by induction, q has at most d roots. And now I claim that therefore p has at most d plus 1 roots, because this is p right here. And what I need to show is that at most d plus 1 numbers you can plug in to get 0. By induction, there's at most, I mean, to get this to be 0, either q has to be 0 or x minus b has to be 0. This is only 0 if x is b, that's 1. And this has at most d roots, so that's the other d. So at most d plus 1 different numbers can make p 0, and that's the end of the proof. Any questions? OK, so as a reminder, this is only true when you're talking about polynomials with coefficients in a field. For example, you could write down this polynomial, but suppose I imagine its coefficients are mod 6, which is not a prime, so this is not a field. This is degree 1, but it has 3 roots, 0, 2, and 4. All make this evaluate to 0. Okay, so that's just a little warning. Okay. One more kind of technical topic related to polynomials, and then we'll do an application. And this topic is called interpolation. Let's say you're given a bunch of data points. And what I mean, something like this. This is like one axis. This means your data has value b1 at a1. And in general, each of these is like an ordered pair, ai comma bi. This is the b, this is the a. And there's a thing you kind of want to do in science. You want to find a low-degree polynomial that fits the data. You know, maybe something like this. Okay, and that's exactly what we're going to talk about now. Fitting a polynomial to data. So let's say we have a bunch of pairs, and I'm going to say we have d plus 1 pairs, where d is some number. And all these numbers are going to be from a field. So you can imagine in your head that they're reals, but it totally works with any field, like the numbers mod of prime. And I also want all the a's to be distinct, because that's like all the horizontal coordinates. I want them to be distinct so that it's really possible to put a polynomial through them. Here's the theorem. If you have d plus 1 points, there's exactly one polynomial p of degree at most d that fits the data, that has all the desired evaluations. Okay, so like, for example, if you have 2 points, it's like saying there's a unique linear polynomial, degree 1 polynomial that fits them. Just kind of a familiar fact. Here d was 2. Okay, so there are 2 things to prove in this theorem. Here's the theorem. Suppose we wanted to prove this. The proof really divides into 2 parts. What would the 2 parts be? At the highest level.
Proving that there is such a polynomial and proving that it's the only one?
Exactly. You want to prove that there's at least one polynomial of degree at most d that does the job. And you also want to prove that there's at most one polynomial that does the job. Okay, and then there's a unique such polynomial. Let's prove number 2 first. Okay? So if you have d plus 1 data points, there's at most one way you could fit a degree d polynomial to them. Okay, that's what I said here. You got d plus 1 data points. There's at most one polynomial of degree at most d that fits them. This is the whole proof. You just say, okay, suppose that there are more than, well, suppose that you have 2 polynomials, p and q, that both have degree at most d and both fit the data. I mean, at the end, I'm going to show that p equals q. Right? That's a general strategy for showing there's at most one object that does something. You show that if you have 2 of them, they have to be the same. Yep?
What if you're pointing to like 0, 0, and 1, 1? So those fit the line y equals x and y equals x squared.
Yeah. So in that case, there's 2 points.
Right.
So d is 1. This is a little trick. Yeah, I mean, maybe I should emphasize this trick. You call the number of pairs d plus 1, and you're looking at polynomials of degree at most d. So if you have 2 points, you're saying there's at most one linear, like degree 1 polynomial that fits them. Okay, so let's say p and q both fit the data. You just let r of x be their difference, p of x minus q of x. Now, if you take 2 polynomials whose degree is at most d, and you subtract them, you cannot suddenly get a power that's bigger than d. So r has degree at most d. But now r, if you plug in all the ai's, you always get 0. Because by definition, p on ai gives you bi, and q on ai gives you bi. So you always get 0. So now you have a polynomial r. It's 0 on d plus 1 different points. And its degree is at most d. So what do we know about it? The only way that can happen is by that big blink tag theorem is that r would have to be the 0 polynomial. Okay, and that means p equals q. Okay. So that was the one part. Now, maybe the more interesting part is that there's at least one such polynomial. That you can always fit to d plus 1 data points a degree d polynomial. Okay, so that's what we want to prove. And to do this, you basically have to give an algorithm. Take in those d plus 1 points. You tell me how to make the polynomial that does the job. So the algorithm for doing this is called Lagrange interpolation, of course, because it was invented by a guy called Waring in '79. And then Lagrange invented it over on the continent 20 16 years later. So here's how it works. Well, let me describe it like this. These are the a's, these are the b's, and you want a polynomial p of degree at most d. Remember, there's d plus 1 points, such that p on all these guys equals these values. So let me do a special case first. The special case is going to be highly helpful and instructive. Let me just imagine these are the b's. I didn't tell you what the a's are, but these are the b's. I kind of promised you that like once we do this one, it'll be pretty easy to do the general case. Okay, so I want a polynomial that on these values has these things. On these values has these values. Now, so the easiest thing is to try to set it up so that it'll at least be 0 on all these d places where you want it to be 0. And you can get that by multiplying together these d linear factors. I'm going to multiply together x minus a2, x minus a3, dot, 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 x minus a sub d plus 1. If I multiply those all, I could imagine expanding these all out, and I'd get a degree d polynomial, right? Because multiplying together d degree 1 things. And this sort of almost works, because its degree is d. And if you plug in a2, this is 0, so the whole thing's 0. If you plug in a3, this is 0, so the whole thing is 0. If you plug in a sub d plus 1, this piece is 0, so the whole thing is 0. So you kind of got the right answer, except probably on the first one. So what happens when you plug in a1? Yeah, you get some weirdo number, right? I mean, you don't really know much about what's going on. You get this crazy number, which is probably not equal to 1. But what can you do to fix this issue? You're almost there. You just need to modify this polynomial a little bit. Yes?
You can take the polynomial and divide by a crazy number.
Yeah, I mean, if this crazy number turned out to be like 17, so like you got answers 17, 0, 0, 0, 0, 0, just divide this thing by 17. And then you'll get 1, 0, 0, 0, 0. So just divide p of x by this number, whatever it is. Okay, and that's this idea. This is the answer. This works. I call this polynomial s sub 1 of x. There's the thing on top, and then this thing is just a number in the bottom. Okay, so the numerator is a polynomial of degree d, and the denominator is just a field element. It's a number. Now, actually, there's one little thing we should have checked. You're not allowed to divide by 0. So how are we sure that this thing is actually not 0?
Because
Well, how about? Yeah, I mean, this is only going to be 0. You're multiplying some things together if one of these is 0. But, it's part of the specification of the problem that all the AIs are different. OK, so this is just a big polynomial divided by a number, which is a polynomial of the same degree. And I'm going to call this the selector polynomial S1 for A1. Because it's, it just means, by that I just mean it has these values. Okay, so this is actually the main step of the proof. Is there any question about it? Okay, so fine. Let me give you, before we go straight to the general case, let me give you this data. How could you get a polynomial that had these values? Well, I hope it's pretty obvious, right? You just do the same thing we just did, but like for 2. Okay, so you multiply together x minus a1, x minus a3, minus a4, etc. Divide by what you get when you plug in a2 to like cancel this thing down to 1. And I'll call this the selector polynomial S2. OK, we can do that for S3 and so forth and so on. So even for this data, we can get a polynomial that fits it of degree exactly d in the same way. OK, so we just solved d plus 1 special cases of this problem. That's a lot of special cases. So let's go straight to the general problem now. How are we going to do this data? Does anybody know this trick? You've answered a lot of questions. Does anybody know how to do it based on what we've done so far? OK.
B1 times S1 plus B2 times S2.
Yeah.
All the way to B1 times.
Exactly, yeah. So here it is. It looks complicated, but it's not. We have all these polynomials, these selector polynomials, S1 through SD plus 1, that are 1 on a particular point and 0 elsewhere. So if I want this data, let me multiply S1 by B1. That'll have values B1, 0, 0, 0, 0, 0, which is good. I multiply B2 by S2. That other polynomial will have values 0, B2, 0, 0, 0, 0. You know, dot, dot, dot. If I do the last number times the last selector polynomial, I'll get the polynomial which is 0 everywhere except it has the right value here. So now I have d plus 1 different polynomials. Each one kind of gets one of the values that you need, and it's 0 elsewhere. So then if you add them all up, you get the polynomial that has all the right values everywhere. OK, and these all have degree at most d. Actually, all the s's have degree exactly d. So when you add them all up, you get a polynomial of degree at most d. Because actually, potentially, some of the higher degree stuff could cancel out. That's OK. OK, so in the interest of time, I think I'm going to not go through this example very carefully. You can look at the slides afterwards to see the example. So here's d is 2. The field is f11. And I just say I want a polynomial p of degree at most 2 that has values 1 at 5, 2 at 6, 9 at 7. So I literally just do the polynomial. First, I got to get the selector for 5. So I make this thing, which is 0 at 6 and 0 at 7. And maybe it doesn't have the right value here in order that it's 1 on 5. But then you plug in whatever that is. You get 6. OK, let me more or less skip it. But this is 1 at 5 and 0 elsewhere. This is 1 at 6 and 0 elsewhere. This is 1 at 7 and 0 elsewhere. And so now if I take 1, 2, and 9, the desired values, multiply and add appropriately, expand it all out, reduce everything mod 11. You can check this in your dorm. You get finally this polynomial. It has degree at most 2, and indeed its value at 5 is 1, its value at 6 is 2, its value at 7 is 9. OK, well, that was a little fast, but that's how it goes. Does it really work? If I plug in 5 to this, I get 3 times 25 is 75, plus another 5 is 80, 89. Yeah, mod 11, subtract off the 88, you get 1. So at least the first thing worked. OK, any questions? OK, so this is the theorem again. D plus 1 data points. There's exactly one polynomial of degree at most d that gets them. And that leads to the following interesting idea. Actually, when you eventually work with polynomials, I mean, everything in this class is about computers. You store them on computers. And to store a degree d polynomial, you really need to store d plus 1 numbers. But actually, there's 2 different ways you can do it. How can you store a degree d polynomial with d plus 1 numbers, field elements? Well, first is you just store the d plus 1 coefficients, right? There's the coefficient on the 0th power, the 1st power, the 2nd power, dot, 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 up to the dth power. But another way you can do it is just store p's values at d plus 1 different locations. And that actually uniquely determines p. That's what the theorem, in a sense, just says. So if I have, how do I go from representation 1 to representation 2? If I know the polynomial because I know its coefficients, and I want to get its values on d plus 1 different places, well, I can just evaluate the polynomial by plugging into it. On the other hand, suppose I have a polynomial and I'm keeping track of its values at d plus 1 different inputs, then I can get like the polynomial in its usual representation with the coefficients by doing this Lagrange interpolation. That uniquely determines what that polynomial is. OK, so that's the end of the theory of polynomials. In the last 25 minutes, we'll do an application. In this application, actually, we're going to talk about it in the next lecture, too. Is to a topic called error correcting codes, which is a very important topic in computer science. It's the problem of how you can take data and add some redundancy to it so that even if some of the data, the redundant data gets corrupted, you can still recover what the original thing was. So this comes up in several scenarios, like if you want to send a message to a friend over a channel that's kind of like noisy, like you're sending a signal to the Mars rover or something, you want to add some redundancy to it so that, even if it's corrupted by noise, the person at the other end can decode what you meant. Or if you're like storing some data on a disk, and you worry that the disk might get like scratched or something, like it's a CD, that was like this old thing for storing music. You want to set it up so that even if it gets scratched and some of the data is corrupted, you can recover what the true information is. Actually, it's sort of the same thing. Like storing information on a disk is like sending a message to your future self. Yeah. So let me tell you a little bit about error correcting codes. Now, I'll take as an example the first example where you're sending messages on a noisy channel from one party to another. Actually, we saw this scenario in the previous lecture when we were talking about cryptography. But here we have different goals. We're not worried about like a malicious eavesdropper figuring out what our information was. That's OK. It's just I'm sending something to the Mars rover. I just want to make sure my message gets across. So in computer science, they always call the two parties Alice and Bob. Actually, Anil deviated from this with his Game of Thrones example. But it's traditional to call the two parties Alice and Bob. So there they are. So let's say Alice has a message that he wants to send to Bob. And I'm actually going to start calling Alice she. But while we're here, he wants to send to Bob. So you might say, like, check out this cool URL. But let me imagine kind of a simple scenario where the channel might corrupt some number of symbols in your message. OK? So how can Alice maybe add a little bit of redundancy to her message or his message so that Bob can still figure out what she's trying to say? OK, and of course, she doesn't want to add too much redundancy. So wants to be efficient about things. OK, so let's say you're trying to send a message, which is like a string. So maybe it's a list of ASCII symbols. And it's Fields Day and Polynomial Day. So we're going to imagine that these bytes that you're trying to send are numbers between 1 and 257. 257 is a prime, which is why I chose it. Since 256 is the power of 2, there actually is a field of size 2 to the 56, but no, 256, but let's just stick with 257. So you're trying to send a message, like a string of bytes, and you imagine each symbol is a number mod 257. OK, this could be the ASCII translation of this. Actually, it's not, but anyway. OK, so you want to send this sequence of numbers. Alice wants to send it to Bob, but she's afraid. She knows that up to k of the symbols might get corrupted. So she wants to add some kind of redundancy to make sure that Bob can still figure out this exact string. So when she broadcasts or sends it on this channel, beams it into space or whatever, or sends it on her cell phone, maybe up to k of the numbers or symbols could get screwed up. And of course, if Bob just gets this, she doesn't add any redundancy, then there's no way he can know what the true original message was. So this is actually a tricky problem. I mean, what Bob really needs to do is, he gets some numbers. He doesn't know that these things are yellow. How does he correct the errors? And in fact, there's an even simpler seeming problem, which still seems tough, which is how does he even detect that there were errors or there weren't errors? He doesn't even know that these ones are yellow. How does he know which ones are right and which ones are wrong? OK, so that's what error correcting codes is designed to try to solve. And we'll give some simple examples here. So the simpler case is a case called erasures. And erasures means that each symbol, when you send it across the channel, either comes through correctly or the receiver gets a question mark. And that means that the receiver knows that he didn't get the right value. It's like a dropped packet or something. He's there was supposed to be something here, but I clearly didn't get it. OK, so erasures are a little bit easier because you don't have to worry about which are the right symbols and which are the wrong symbols. You know that these are all correct. You're missing this information, these two symbols. OK, so the first problem we're going to worry about is how can you devise a code to handle up to k symbols getting erased? So let me tell you the simplest thing you can do, which is not the worst thing in the world. It's called the repetition code. It's probably the first thing you'd think of. So let's say you knew that up to k of your symbols could get erased. Think of k as like 2. So up to 2 of your symbols could be erased. And what do? You just send each of your symbols 3 times. Okay? Or in general, k plus 1 times. So if this is your real message and like k is 2, then in the repetition code, you just send each symbol 3 times. Just like this. 1, 2, 3, 1, 2, 3, 1, 2, 3. And then you're in great shape. Like you've solved the problem because, you go through the erasure channel. Up to k symbols, in this example, k is 2, can get erased. Even in the worst possible cases, like if you erase 2 symbols from a block of 3 that are all the same, well, it's OK. Bob still knows, I don't know, these things got erased, but he still knows that the second symbol overall was supposed to be 114. Okay, and in general, if you repeat each symbol k plus 1 times, and even if k erasures all happen within the same block, Bob can figure out what the symbol was supposed to be. OK, any questions about that? So that's fine. The downside, and this is the, oh, sorry. Let me do another example first. That was the case where we imagine that the channel can erase up to k symbols. What about the trickier case where it doesn't erase symbols, it changes them? So that's trickier for Bob, right? Because he actually just gets a list of numbers between 1 and 257. He doesn't know which ones are right, which ones are wrong. Let's say he just knows that at most k of them are wrong. And you can do a repetition code that survives that too. It's going to be even more redundant. So the trick here is to have Alice repeat each symbol, not k plus 1 times, but 2k plus 1 times. So I'll do an example of that where k is 1. Okay, so I'm going to, again, actually repeat each symbol 3 times, because k is 1. It looks like this again. And now, remember, now it's the trickier case, not the erasure case, but the noisy case, where the symbols can just be changed. And we'll imagine at most 1 can be changed. So maybe when you pass it through the noisy channel, this 223 gets changed, or 114 gets changed to 223. But Bob is still OK here, right? He says this one is definitely 118. This one is 114. This one's 120, 85, etc. So why does this work in general? I mean, this was the example where k is 1. But if k is like 5, why is it OK if you repeat each symbol 11 times? Yeah.
Because for any element, you repeat 2k plus 1 time, and at most it can be corrupted k times, so you just take the majority.
Yeah, like let's do that example with 5. I guess you'll get the general case. So imagine you repeat each symbol 11 times, and the channel can sort of even maliciously change up to 5 values. Well, even if the channel puts all those 5 changes in one block of 11, if you just take the majority value on each block, you'll get the right answer, right? Because it can change at most 5 of the 11 things. The majority will still have 6 copies of the right thing. OK, so this is just what was said. There's at most k corruptions. Bob can decode the message by just taking the majority symbol in each of the blocks. OK, so this all well and good. It works. But the thing that makes coding theorists upset, I mean, you can devote your whole career to error correcting codes, is that it's kind of wasteful. It's pretty redundant, as it turns out. And it's too redundant. So let's think about the erasures case. Let's say we had a message whose length happened to be d plus 1. Now, why did I call the length d plus 1? Well, you'll see. But suppose your message length was d plus 1, and you wanted to guard against k erasures. That was the simpler case where you just got question marks when there was a corruption. Well, we did the repetition code. You repeated each symbol k plus 1 times. So you blew up the length of your message in encoding it by a factor of k plus 1. So you sent d plus 1 times k plus 1 total symbols. OK, and in the noisy case, it was actually d plus 1 times 2k plus 1. So as we always like to ask, can we do better? Well, let's say even imagine that your message was 1 symbol long. It was 1 byte long, so d is 0 here. And you wanted to guard against k erasures. Your message is only 1 byte long. Well, you're going to have to send at least k plus 1 symbols, right? Because if you only send k, like they could all be erased. And then you definitely can't communicate anything. So to send a message with one symbol, you're going to need at least, and guard against k erasures, you have to send k plus 1 total symbols. And that's consistent with this, but the idea is like maybe instead of having basically d times k, maybe you could have d plus k. That would be a lot better. So a dream might be if you have a message of like d plus 1 and you're trying to guard against k erasures, a dream would be like sending a total number of symbols which is like d plus k plus 1 rather than the product. You know, it's kind of like if k and d are kind of proportional, this is like quadratic length and this is linear length. And that dream can be realized. I mean, it's a realizable dream, and this is where polynomials come into the picture. So I'll show you how to do exactly that. So let's say Alice's message is d plus 1 elements over a field. You know, the number is mod 257. Okay, and she wants to encode it in such a way, not blowing it up to too much longer of a string, so that Bob can recover even if they're up to k erasures. Let's say that's her message, so d is 5. Here's what Alice does. She thinks of her symbols as the coefficients of a degree d polynomial in F257 bracket x. Okay, so this is her message. She just in her mind thinks of this polynomial. And then she wants to, it's kind of like now she wants to send this polynomial to Bob. It's the same information. She just wants Bob to also know this polynomial. And the trick is, instead of sending it the coefficients representation, send it in the values representation. And you can add redundancy by sending a few more values than you would technically need for unique specification. So here's the polynomial. What Alice is going to do is send p's value on not d plus 1, but d plus k plus 1 different inputs. And they can just be 1, 2, 3, up to d plus k plus 1. Okay, so that's like kind of the redundancy. And this is a great idea. This is like one of the most fundamental ideas in the theory of error-correcting codes. This is called the Reed-Solomon encoding, named after Reed and Solomon. There they are, Irving Reed and Gustav Solomon. Okay, so here's the simple idea. Bob gets, well, this goes across the channel, these d plus k plus 1 symbols, or numbers, mod 257. And at most, k of them can be erased. So what Bob sees is he still gets p's value on at least d plus 1 different points. Because at most, k of these get erased when it goes across the channel to Bob. And so now Bob knows the polynomial's value on d plus 1 different points. And you know, he knows that Alice is thinking of a polynomial of degree d. So he just uses Lagrange interpolation and finds the unique polynomial that Alice had to have been thinking of. Does it make sense? Any question? Yeah, so that's pretty cool. So I'll even do a little example to illustrate it. So whenever I do anything to do with math, I always do it with this program Maple, which is also similar to this other program called Mathematica. They let you just do math with a computer. You should definitely always use it. And it's going to actually make it like live and like type everything, but then I would probably like make a mistake. So I just like kind of did a screenshot of me doing it. So it actually doesn't prove anything, but anyway, here's the demo, if you will. I don't know if you can even read this, but in Maple, you know, you load some packages. In my example, as d equals 5 symbols, and k is 3. That's the number of possible erasures. And like here was our favorite polynomial, right? This message was actually 118, 114, 120, etc. So I told Maple to make this polynomial out of it, so of degree 5. And then Alice, she sends to Bob just the evaluation of this polynomial on the numbers 1, 2, 3, 4, 5, 6, 7, up to 9. Okay, I just told it to evaluate the polynomial, always mod 257 on those values. It gives me the list of what Alice sends. So there they are, 67, 171, 41, etc. Then I told it to pick 3 numbers between 1 and 9, so it picked 2, 4, and 8. Those are the erasures. And then I told it, Bob gets, just delete from this list the 2nd, 4th, and 8th element. So this is what Bob gets. Bob sees 67, 30, 41, 73, etc. And then, Maple has a built-in algorithm for doing this Lagrange interpolation, which is convenient. So I told it to do that. And you can see it actually builds the polynomial here just as we did. So it's kind of in an unexpanded format. I told it to expand it. And, voila, it got the original polynomial back. So that's how the algorithm goes. OK, any questions about this? OK, great. So cool. So we sort of got a cool solution for the problem where the channel erases symbols. It's kind of not only just dropped packets, but the packet was dropped. The symbol is dropped. The trickier thing is corruptions. OK, but we're going to sort of semi-solve that too. So, corruptions are trickier because Bob doesn't know where the errors are. So you have to have more redundancy. But we're going to have a similar amount of extra redundancy. In fact, Alice's strategy is just going to send P's values on a few more points. With K erasures, we did D plus K plus 1 evaluations. When we're trying to guard against K corruptions, we'll do D plus 2K plus 1. And that's sort of the same amount of savings. Remember with the repetition code, to guard against K corruptions, we had to do D plus 1 times 2K plus 1. That was the majority thing. D plus 1, the length of the message, times 2K plus 1. And now we're getting, more like the sum. D plus 1 plus 2K plus 1 minus 1. OK, so this is how Alice is going to guard a message of length D plus 1 against K erasures. And now, why is this a pretty good idea? Let's think about it. So Alice sends Bob P, which is sort of the same as the message. P is the polynomial whose coefficients are the message symbols. She tries to send him this polynomial. There's at most K corruptions. So what Bob kind of gets is he has the correct value of P on at least D plus K plus 1 different inputs, different input points. But there's a problem because he doesn't, so it kind of looks like this. Maybe some of the symbols get corrupted. But the problem is he doesn't know which of the values are bogus. He looks at his list of numbers. It's not like number, then the word bogus or something. It's just like a list of D plus 2 plus K, D plus 2K plus 1 numbers. And he doesn't know which are the good ones and which are the bogus ones. Now he's actually, in some ways he's in better shape though, because he has more correct values than he had in the erasures case. But on the other hand, he's suffering because he doesn't know which are the wrong answers. OK, so he gets this situation. He thinks about it. And here's one thing that he can do. So he knows that P of x is a polynomial of degree at most d, which disagrees with this received data at most k positions. He doesn't know which positions, but he knows that P's true values are the same as the values he got in the list, except at some k positions. And here's the theorem that I want to show you, which is quite easy. P is the only such polynomial of degree at most d that agrees with the data to that extent, that disagrees with the data on at most k positions. So what that really means is at least Bob can, in principle, figure out the answer. There's a uniquely well-defined answer, which is the message that Alice was trying to send. Maybe it might take him a long time to figure out what that unique polynomial is, but at least in principle, he can solve the problem. So let me at least prove this theorem to you. That P of x is the only polynomial of degree at most d, which disagrees with the data he receives on at most k positions. OK, here's the proof. So imagine Q of x is another such polynomial. So that P of x and Q of x are both degree at most d. They both almost agree with all the data. They're wrong on at most k positions. What am I going to show? What's the last line of the proof going to say?
Equal P
Yeah, therefore P equals Q. I want to show that there's at most one polynomial that has all this good agreement. So now P of x and Q of x, if you look at their values on the first d plus 2k plus 1 points, P is almost in all positions equal to this received list, and Q is also almost equal to this received list. So P and Q must more or less be almost always equal to each other, right? If P disagrees with a fixed list P agrees with a fixed list except that at most k positions, and Q agrees with the same list except that at most k positions, then P of x and Q of x disagree with each other except that at most 2k positions. Right? Okay, so just by subtraction, that means they agree with each other on at least the total number of evaluation points minus the number where they disagree. C plus 2k plus 1 minus 2k, which is d plus 1. So now we're in good shape. P and Q are polynomials that agree on d plus 1 different positions, and they have degree at most d. So therefore, they're equal by this blink tag kind of theorem, right? Because, well, we saw this before. If you have, d plus 1 data points, there's at most one degree at most d polynomial that fits all that data. So if you have two polynomials of degree at most d, and they're the same at d plus 1 positions, then they actually have to be the same everywhere. And that's by considering p minus q, which is another degree at most d polynomial, which is 0 on more than d positions. So it has to be 0. Okay, any questions about this proof? So that's also pretty cool. It shows that with this, again, very little redundancy, Alice sends a message of length d plus 2k plus 1. Bob, at least in principle, can figure out Alice's message. There's only one thing she could have been trying to send, given what he received. Now, there's kind of a problem, which is that, okay, in principle he can figure it out, but in practice, he's got to figure it out. So how can he do it? He knows that there's some low-degree polynomial that mostly matches the data, but how does he find it? He can't just do Lagrange interpolation on the first, d plus 1 points, because that might contain some errors. In fact, for any set of d plus 1 points he might try, he might get some error. Now, there is some d plus 1 set of points that have no errors, because this is the total number of values, and there's at most k corruptions. So actually, there's some d plus 1 points where if he did interpolation, he would get the right answer. And at least for brute force, he could do this. He could try all these different polynomials, get kind of like a candidate, and then check if it does agree on most of the positions, if it does agree on this many values. Unfortunately, that's a brute force algorithm, and it takes exponential time. But you can turn it into an efficient algorithm. I mean, you need some smarts. And this smarts was actually done by a famous coding theorist from the 60s, Peterson, and he gave a polynomial time algorithm for finding this polynomial. It runs in cubic time in D. So it's tricky, but he does it. I mean, given this list of data for which there's a polynomial that matches most of the data and is of degree at most D, he shows an algorithm for how to find it. And that was cool. And then actually, D cubed is not so practical, but Berlekamp and Massey made a lot of practical improvements and made it, really practical. And indeed, this Reed-Solomon coding scheme is very, very practical. And also, if you ever see this guy in the hall, you can give him a high five. He taught 251 last semester. He works on a lot of this stuff, and he actually, in some sense, developed some efficient algorithms that can correct more than k corruptions, even with the same amount of redundancy, which what I said is actually impossible, but he figured out a different way to get around it and did some cool stuff. So just let me conclude by saying these are truly practical codes and applications of polynomials. If you ever get a package, the thing looks like this, right? Or if you ever see a QR code, it looks like this. These are literally Reed-Solomon codes. They're just kind of drawn in a two-dimensional way. And they're really literally designed so that if your bad camera looks at it and kind of screws up some of the pixels, as long as it gets enough of the pixels correct, it can decode the data. So there's your Reed-Solomon codes and polynomials right there. Okay. see you on Tuesday.